we welcome everybody at this public session of Quantum Talent Showcase. We normally had 4 presenters, and then with time we decided to give more time for presentation. 3 presenters last time, and for today we had 2 presenters scheduled, but one of them broke her arm, so she's unavailable. And therefore, for today's session, which is still a public session, and so we're very happy that everybody's here, we have Vikas Buchemmavari from the University of New Mexico, the Center for Quantum Information and Control. And the way we're going to run this, we're going to say a few words to introduce him, and then he's going to go and do his presentation. We have plenty of time for this. I think it's going to be recorded, and then we're going to post it later. My name is Adrian German. I'm from Indiana University Quantum Science and Engineering Center. And I'm assisted today by, Luis?
Reza.
Yeah, but the family name, I forgot. Reza Hedayati?
Hedayati, very good, yes.
From Nubis AI. Would you like to say a few words about you, Reza, just because you're going to take over of this showcase for next year, just a few words about your company and...
Sure. Yeah, Nubis AI, we started a few years ago, a startup company in the renewables energy. And over the last year, I've been trying to transition into the quantum world. So happy to be here and looking forward to taking over as of next year.
Very good. So our first presenter for the day is Vikas Buchemmavari. He's a PhD student working with Ivan Deutsch at the University of New Mexico. He completed his undergraduate studies in physics at the Indian Institute of Technology, Madras. The title is on the screen. It is Entangling Quantum Logic Gates in Neutral Atoms via the Microwave-Driven Spin Flip Blockade. So with this, welcome, Vikas, and thank you for agreeing to present today. I'm going to stop sharing, and if you can share the screen and start the presentation, that would be wonderful.
Thank you, Adrian. All right, so I am Vikas Buchemmavari, and today I'll be talking about a recent project that we finished, where we try to improve the neutral atom quantum computing. So, as I said, our area of interest is neutral atom quantum computing. You might have heard about ion traps or superconducting qubits, but in the neutral atom quantum computers, focused laser beams are used to trap and levitate individual atoms, like shown in this artistic picture here. These green lines. Can you see my cursor on the screen?
Yes, I can. Yeah,
okay,
yeah. You're in the middle.
Yeah. So these green lasers represent the lasers, and these circles represent the atoms. And you hold these atoms in these individual focused laser beams called tweezers. And these tweezers hold individual atoms, and then we put quantum information in them in the electronic levels of the atom. You might have heard about qubits, which are bits, which can be so quantum bits can be 0 or 1 or something in between. So for example, if we are using C-SHIM atom, its ground state looks something like this. There is a total of 16 levels, but we choose 2 of them to encode our information in it. If you've ever heard of C-SHIM atomic clocks, these are the 2 states that are used in the atomic clock. So by storing information in these 2 states, they can be very long-lived. They do not decohere or decay pretty fast, which is very good. And these 2 levels are coupled by a microwave frequency. So if you want to, say, take the population from 0 and put it in 1 or do something like that, you need a microwave field of that frequency to do these things. You can also use Raman lasers, but that's a different thing. But the idea is that using microwave frequencies, you can modulate or control these qubits. So our motivation here is that neutral atoms are not very good at entangling qubits. The reason why you heard about ion traps and superconducting, but probably not about neutral atoms in the past, is because ion traps and superconducting qubits have very, very high gate fidelities, that is either manipulating individual qubits in 1 qubit gates or entangling qubits in 2 qubit gates or entangling gates, as we call them. So while neutral atoms have a lot of other advantages, for example, you can put hundreds of atoms at the same time in a trap. These days, people even do thousands of atoms. And in ion traps and superconducting qubits, that's not easy. The scaling part is not easy. So neutral atoms, you can scale very fast, but the problem is to do this each individual gate, it's not very easy. So our idea, our motivation is to improve that part of neutral atom computing. And to be fair, 2 qubit gates are the most important thing in any quantum computer, because without entanglement, quantum computers are not going to be very effective. So our motivation here is to build better 2 qubit gates in neutral atom quantum computing. I'll actually give a cartoonish summary of our idea here before I go into any mathematics at all. So as I said, you hold these individual atoms using lasers. And currently, the way we do single qubit gates is by using these microwave frequencies on each individual atom. To do the 2 qubit gates, so these microwave gates are actually very, very easy. And people do these with very high fidelities of up to 99.9% fidelity, or sometimes even more. So this part is not the hard part. The hard part is the entanglement, where you need to get 2 atoms to talk to each other and get entangled. These are done using UV lasers. And this part is tough because UV lasers are notoriously noisy. So controlling these UV lasers is not easy. And that results in a lot of experimental noise. So our idea is something like this. You have 2 atoms that you want to entangle. You turn on a background UV laser and you just let it be. You do not control it. All it needs to do is stay in the background. And once the atoms start talking to each other, you use microwaves to do the control part. Now you shine an extra microwave field on it and do some kind of a control. For example, you can do a waveform of the microwave phase that looks something like this. Experimentally speaking, implementing things like this is very easy. And by doing this, you can implement the same gate, but now you offloaded the control part into microwaves. That is the idea. So you've taken the control part from UV lasers and put it into microwaves. And microwaves are a much more mature technology. They're simply slower, so they're easier to control.
Feel good and stuff. You do.
Okay. So because microwaves are easier to control, we expect these gates to have good experimental fidelities. Even theoretically speaking, these gates can have very high 99.9% or so fidelities. Of course, the experimental fidelities will be lower, but we'll see. Our paper is available on arXiv. You're welcome to read it. Okay, now we can go into the details. Also, I think you can stop me at any time if you have any questions. All right.
I don't have a question. I just wanted to encourage everybody who's not a speaker to mute themselves. So good. Thank you.
All right. So if you read anything about neutral atom computing, you probably heard about Rydberg states. Rydberg states are just very high-lying electronic states in an atom. For example, if you take something like a cesium atom, in its ground state, it's in the n equals 6 level. The principal quantum number equals 6. For hydrogen, that is 1. But if you want to be in a Rydberg state, you need to hit something like n equals 60 or something like that. The idea behind these Rydberg states is that if you have a normal atom of cesium in its ground state, it looks something like that black dot on my screen right now. You probably can't even see it. But if you put it in a Rydberg state, it's about that big. So these Rydberg atoms are massive compared to the ground states of atoms, which means that they have electric dipole moment, so they interact with each other. That's the big idea behind Rydberg states. And these states are not bad. They have decent lifetimes. of hundreds of microseconds, which is more than enough to do the quantum computing that we do right now with very small, very low depth circuits. So, but because of this very large size, they have a very strong interaction with each other. This is important because neutral atoms, by the virtue of being neutral, do not talk to each other at all, which is good because that means that they're not very noisy. They keep information for a very long time. But to entangle them, we need something else, which is why we use these Rydberg states to entangle two atoms. So how do we use this Rydberg interaction in entangling atoms? Let's say you have an atom. In the ground state, you have the qubit states 0 and 1, and you have a Rydberg state high-lying somewhere. You can couple one of the qubit states to the Rydberg state using a UV laser, or you can also use like a 2-photon transition, but we are considering UV lasers in cesium. If you have two atoms right next to each other now, this is a complicated diagram, but what I've done is I've taken these two atoms and written their energy levels in a slightly different way. So while this diagram is complicated, all you need to focus on is a couple of things, which is that if you have two atoms in the one state, notice that if both of your atoms are in 0, 0, it means that nothing is going to happen because your laser is not coupling. If you have only one of the atoms in the one state, the diagram looks exactly like your single atom. This single diagram and this is exactly the same. But when you have both of the atoms in state 1, that's when the interesting stuff happens. The first thing is that you get this enhanced Rabi frequency. The frequency with which their population gets pumped out is higher here. But more than that, because Rydberg states interact with each other, this double Rydberg state has some peculiar properties, and it gets this nonlinear detuning. It is not where it's supposed to be. And this interaction energy shows up right here in this level diagram. So if this interaction energy is very large compared to the driving frequency of the laser, the Rabi frequency, you will never pump population into this double Rydberg state. This is known as a strong blockade because this no population can be pumped into this state. And usually, experimentally, this is the condition that people work on. The blockade, the interaction energy is very, very large, so you simply never pump population into this double Rydberg state. This is known as a Rydberg blockade, if you've ever heard that name. And the idea is that you can use this to create entangling gates. The seminal gate was introduced in 2018 and 2019 from Misha Lukin's group in Harvard. But what they do is, because of this Rydberg blockade, you can simply ignore the double Rydberg state. So all of your dynamics looks like two levels. So there is a two-level system here, there is a two-level system here. So we can think about these in block spheres, which is easy to imagine. So the idea is, if you're pumping population out of the computational states, that is the 0, 0, 0, 1 and 1, 0 and 1, 1, when you drive populations with this UV laser, you can only push them out, but you cannot push them in between each other. So what you do is you push them out and you pull them back, but at the end of this process, they would have accumulated phases because of quantum physics. And the idea is that if you do this in a proper way, these phases will be such that this is a Control-Z gate, which is the quintessential entangling gate in quantum circuits. So the way they did it, the original idea, was to use two pulses. First, a single pulse does something like this. So in the case of 1, 1, the Rabi frequency is higher by this factor of √2. Whereas in the case of 1, 0 and 0, 1, it is smaller. So the population in 1, 1 finishes a full rotation. I hope you can see the GIFs playing here. Whereas in 0, 1 and 1, 0, they only do a partial rotation. And then you do a second pulse, which finishes the rotation in 0, 1 and 1, 0, but does another full rotation for 1, 1.
So we actually reserved the room.
Okay, I'll get it.
So, are you gonna be here for long?
Yeah, I can get it in just a minute.
Okay, all right, thanks.
Sorry, I've been kicked out of my room. I'll move in just a little bit.
No problem.
But yes, so the idea is that at the end of this process, the populations return and they get the right amount of phases to do a Control-Z gate. But then recently there has been advances in this research area. And instead of using two different pulses, we use a single pulse as shown in this diagram here. And what it does is this single pulse does two different kinds of rotations on 0, 1 and 1, 1. And in the end, does the same thing that those two pulses would have done, but slightly faster and in a single pulse. And this is a very interesting thing because you're using lesser time. And you're also have other advantages, like you don't have to turn off the lasers in between. And to find these waveforms, people have used quantum optimal control algorithms, such as GRAPE, or gradient ascent pulse engineering algorithm. And these algorithms are very interesting because you can take any system and try to find waveforms that can do particular tasks for us. We use these algorithms extensively, and in fact, I'm going to use these in my project. So far, I've only shown you work that has been done by other people, but I'm going to show us a result that we've produced. One result is that most people work in the regime where the interaction energy is very, very large. So the ratio of the interaction energy V to the Rabi frequency omega is going to be something like 10 or 100. But we showed theoretically that if you can somehow get this ratio to be smaller, you'll actually not lose much. You'll, in fact, your gate times will be slightly faster. So this is very counterintuitive to say that weaker interactions can actually result in faster gates. But it is true, and there is precedence because there is a lot of work from Paul Yessen's group in Arizona and Ivan's group, who is my advisor, where they've shown that if you're controlling spin systems, the best scenario is when the interaction energy is approximately equal to the driving frequency, which is very counterintuitive, but there is some very interesting physics behind it. So we're seeing something analogous to that. So the cost of this is that you pump population into the double Rydberg state, which was before useless. But that's a smaller problem. So we also use this in our project in a little bit later. All right. So now the question is, if there is an alternative, instead of using UV lasers, can we use something else? That would be good because microwaves are something like 100,000 times slower than UV lasers. So your electrical components simply work better because they're oscillating at slower frequencies. So microwaves are a much developed technology, experimentally speaking. So anything we can do with microwave will generally be better in terms of control fidelities than UV lasers. So we are motivated by this paper from about a decade ago now, where people at Sandia National Labs used something called UV Rydberg dressing, where they take a state and then dress it with a Rydberg laser. And what that does is gives this dressed state the properties of a Rydberg state, which and then by using microwave control, you can create entangling gates with very high fidelity. At the time, in fact, these were state-of-the-art fidelities. So inspired by this, we want to create an entangling gate which does something similar. All right. before I move on, I hope everyone's following along and stop me anytime to ask questions again. So we look at something called dressing. Dressing simply means you shine light on atoms. It's an old term, but that's what is called dressing. So let's say you have two atomic states, A and R. If you turn on a laser that couples them, but not resonantly, so the frequency of the energy difference is different from the laser frequency, then you get something called dressed states, which are basically the eigenstates of the Hamiltonian. And there will be intermixing of the two states in these dressed states. For example, this A becomes a dressed A, this A tilde here, and it will have the properties of both the A state and the R state. And if we take population in a different state and then couple it to the one of the dressed states, you see some really weird effects, like some of the population gets coupled to the one state and the other population gets coupled to the other state. But the idea is that if you are in the right regime and if your detunings are of the right order, you'll only couple to the dressed state and you'll not couple to the other dressed state R. So, and these dressed states get something called light shifts, which is their energies get moved by a little bit. And this is the whole thing about dressed states. So you shine a laser on your atom, which means that the levels of the atom get slightly changed and they move around in the energy landscape. There's someone in the chat. Oh, so someone asked me to define fidelity. That's a very good question. Fidelity is basically, you can think of it as at what percentage of the times does your operation do what you want it to do instead of doing something else. For example, 99% fidelity means that 99% of the time it will do what you want it to do, but 1% of the time it does something else. Now, a 2-qubit gate fidelity means that what percentage of the time your 2-qubit gate does what you want it to do. Now, 99% might sound like a lot, but the thing is, in a single circuit, there'll be hundreds of atoms, which might go through like many 2-qubit gates. So if you have 99% fidelity, which it means that at the end of your circuit, you're going to get right answer like 1% of the time. So that's why pushing these numbers to 99.9 or 99.99% is very important in quantum computation. So I do not understand the stabilize level part, but these energy levels move around in because of these lasers. That's what I'm talking about.
So I was going to wait until later or at the end and ask Keith to perhaps clarify his question. But if Keith wants to say something now, that would be a possibility.
Yes, I'm sorry. Just coming into this, I think you hit it right on the head. Stability is in terms of the, your assurance that it's actually behaving within 3 nines, 5 nines of accuracy. I get it. You explained that very well.
All right, thank you. Yeah, so but there is one problem with Rydberg states. As I mentioned before, they don't live forever. They decay with some rate. And the idea is that the Rydberg states decay at some rate, and these dressed states also inherit that. They also decay. So, and there is some interesting stuff here. For example, you can modify how strongly you dress an atom by changing this detuning, or the difference between the frequency of the laser and the frequency of the energy gap. And if you increase that difference, that's called weak dressing. And what it does is, if you keep decreasing the dressing strength, you basically go back to your normal states. Your dressing effect becomes nullified. If your detuning is 0, that is you drive the laser at exactly the same frequency as the energy gap, then that is called the strong dressing. And there, your states will actually be equal mixtures of both. But the idea is that there is this weak dressing and strong dressing. And if you're in the weak dressing regime, your states will be very similar to the undressed states. So the difference is going to be not very large. So overall, what happens when you dress these states using Rydberg lasers. Let's say you have two atoms. And what we do is your qubit states are 0, 1. And then we choose a third state, which we call an auxiliary state. It's going to be useful in a little bit. And we dress this auxiliary state with a Rydberg laser, as shown here. And we can couple this auxiliary state to one of the qubit states with a microwave frequency. Now, if you take two of these and put them next to each other and look at the level diagram, it looks very horrible, like I've shown here. Don't worry about it. All I mean to show is this is a complicated question and we tackle this in the paper. But the idea is that you can simplify this picture by looking at particular areas and looking at the Hamiltonians and then diagonalizing them. You diagonalize this Hamiltonian, you get a simpler picture. You diagonalize this part, you get a simpler picture. And in the end, your level diagram looks something like this. You have the dressed auxiliary state over here. And you have the computational states here. And then you'll have this weird interaction energy J in here. Now, this might, you probably don't remember this, but the picture I showed at the start of this presentation was something like this for the optical scenario. So the idea is that now we can do this, and you probably see how these are very similar. The idea is that now you can do anything that you did in the optical scenario, now you can do, but with using microwaves as shown here. So this is the big idea. Anything you do in optical scenario, you can do with microwave control instead. And this might be a very powerful tool in experiments. So that is the big idea. And now we look at a specific example of how to do a particular kind of a Rydberg of an entangling gate. All right, so the idea is something like this. You have microwave coupling one of your qubit states to this dressed state, and your diagram looks complicated. There is a lot of numbers there, symbols there, which I'm not going to go into. But all we want to do is to create an entangling gate. So in an experiment, this is what is going to happen. You take the population in your atom and you do something called shelving, where you take the population and put it all in the same area, in the same hyperfine manifold, so that when you dress the atom, these don't get disturbed. So in the ground state, you choose one of the states as an auxiliary state and dress it with the Rydberg laser. And then use microwaves to do an entangling gate whose level diagram looks something like this. That's the idea. That's the whole idea. All right. I'm hoping, I'm guessing there's not a lot of questions. I'll move on. Right. So now that we can do these gates, how good are they? That's the question. And to do that, we need to talk about how these Rydberg states decay. So as I said, these dressed states have Rydberg character, and Rydberg states decay, so these dressed states also decay. And what we can do is, using mathematical methods like introducing a non-Hermitian term in the Hamiltonian, we can simulate these gates and figure out their fundamental bounds. You can say that this gate cannot be better than, say, 99.9% or 99.8% fidelity, because the Rydberg decay happens at a particular rate, and we are driving these populations at a particular rate, etc. So using this, we can put a fundamental bound on the gate fidelity we can achieve, and we'll look at that. So we want to see if the fundamental fidelity gets better or worse, if we can improve it. These are the important questions. So as I've showed you before, there's a range of dressing strengths we can look at. You can do strong dressing or weak dressing. And if you do strong dressing, this interaction energy will be very large. But as you go to weak dressing, this interaction energy falls pretty fast, which is probably not very good, because usually interaction energy falling is not very good. Do you have a question, Adrian?
No, I just opened the microphone because
Oh, see.
so there is a question in the chat, but I was thinking of asking it a little bit later. The question says, please explain each diagram and then the whole protocol, which is you'd go back to the diagram. So, and then what I wanted to add to that was a question about the shelving operation. If you
Yes.
think that it is essential and if it can be avoided or you know, it's fundamental.
Yeah, so that's a very good point. Yeah, so we do this weird shelving thing because of a couple of reasons. So the first thing is the way we store our population is by putting them in these two different hyperfine manifolds. So these are the two states which we define as the qubit states, 0 and 1. But the thing is, if you want to couple to a Rydberg state, let's say if you couple this one to a Rydberg state, you'll start pushing the population into the Rydberg state. We don't want that. We want to do dressing on an empty state. So we do the shelving where we use microwaves to put this population in the 0 state into this state here. Right. So once that is done, what we can do is we can turn on a Rydberg laser, which couples this state to a Rydberg state with a small detuning. The thing is, I've not shown this here, but if you couple this state to the Rydberg state, you kind of automatically couple this state and also this state, etc. You cannot distinguish between them, which is why it's very important to put all of the population in the same manifold and then couple to the Rydberg state from the other manifold. And the idea is that once you do this, this A state becomes stressed. And previously, to control the qubit population, you would have coupled the states 0 and 1 using microwaves. You can use the same microwave to couple these two states now, because it's basically the same state. And so now you can use this microwave to implement any entangling gate. The same microwave that did 1 qubit gate now can do the 2 qubit gates. That is why this we do this shelving operation. And so once you do this dressing in two different atoms, the two atoms look something like this side by side. And then if you go into a slightly different basis, the level diagram looks something like this, with this interaction energy in here, which is the non-linearity. Basically, if this J was equal to 0, there would be no non-linearity and you wouldn't be able to create entanglement. But this non-zero J will help us create entanglement. I hope that answers.
Yeah, so that's very good. This was prompted by the comment in the chat by Abdullah Ali Fargi or Fargi. Now, if you would like to say something in case you have something to add.
Yeah. So so one thing is you don't need to do this shelving always. We are looking at cesium, which is an alkaline atom, which has a particular kind of a structure. So we need this. But if you did these same experiments in something like ytterbium or strontium, you probably wouldn't need to do the shelving at all, because there the clock state, the electronic structure is very different. So there are possibilities where you don't need these shelving operations at all. We are in fact looking at it in collaboration with some experimental groups. All right. Yeah. So what we are looking at is this fundamental bounds on fidelity to decide if our entangling gates are good or not. So as I said, when you go into weaker dressing regime, the interaction energy J falls pretty rapidly, which is not very good. There is also another effect where if you go into weak dressing regime, your coupling strength actually becomes stronger, but I'm not going to go into those details because for brevity's sake. But the idea is that as you go into weaker dressing regime, your interaction energy falls pretty fast. So this 0 means strong dressing. And as you increase the absolute value of the detuning, that is weaker dressing. So I'll remind you that I showed this plot a while ago where I showed that if your interaction energy is on the order of your driving frequency, it was actually not very problematic. It didn't have any disadvantages. The gate time actually was slightly faster. So having a smaller interaction energy is not necessarily a problem anymore. So we combine these two ideas and we try to figure out which kind of dressing is the best. And heuristically, by looking at this plot I just showed you, what one would think is if V equals omega L, that gave you the best gate times here. So in this scenario, probably J equals omega microwave will give you the best scenario. So you can look at that. So you, by deciding on this condition, you'll get how much dressing strength you need, and which is determined by the dressing detuning. And that's it. We show in the paper that this actually works, and this actually gives you the fastest gates and also the best gates. So for example, here, I have the detuning in megahertz in the x-axis and the gate time on the y-axis. And you can see that at around 0.5 megahertz of detuning, you actually get the fastest gates, which is equal to the condition I just talked about. And there is some really interesting reasons for why this happens. For example, if you're in the strong dressing regime, basically you're wasting some of the interaction energy. If you're in the weak dressing regime, the atoms are simply not interacting fast enough. But in the middle, you kind of get this sweet spot where you get the best of both worlds and get the fastest gates. Now, if you look at the fundamentally limited fidelity, that is the maximum fidelity you can get while while including the Rydberg decay in your dynamics, that also is maximized at the same point. This is usually expected in physics experiments where the fastest ones tend to be the best. So this is the idea. So basically, this your dressing strength should be neither strong nor weak, but in this middle regime where it is equal to the driving strength. That gives you the best possible gates. And if you use the quantum optimal control techniques to find waveforms that implement the gates. These are numerical methods that help us implement whichever unitary we want to implement on a quantum system. And the microwave phase waveform looks something like this. And these are very easy to implement. Microwaves, these have been done for many years, almost decades now. So this part is pretty easy. So this is the big idea. But there was another interesting side effect, which that we found during this research, which was that there is noises in your gates because of other things like the atoms moving around. For example, a big thing is called Doppler noise. You probably know about how ambulances you hear ambulance noise differently when they're coming towards you and away from you. Similarly, these atoms are moving around, so they see the laser light differently if they're moving towards the laser light or away from it. So that results in a frequency noise in the laser. So they see a different frequency than we are actually shooting at them. So this is called Doppler noise, and this is a pretty big problem, especially in UV lasers, because their wavelength is very small, which exacerbates the problem. And there is a lot of literature on this, and in our paper, we delve into this deeply. If you look at the whole Hamiltonian and the level diagram, it looks something like this, where the Doppler noise results in coupling between something called the bright and dark states. If the experiment was perfect, you would only have the bright state, the dark state would be dark, like it would never enter the experiment. There is other problems with it, like there will be detuning noise, etc. I'm not going to go into the details here, but the idea is that there's a lot of these noises that can happen. But the thing is, we are looking at dressed states, and dressed states are simply eigenvectors of Hamiltonians. So you take this whole Hamiltonian, and then you diagonalize it to get the dressed state. And when you diagonalize it, all of these errors get funneled into the final dressed state structure. So if you have 6 different kinds of errors, in the end, you will only see one kind of error, which is what is the energy level of this stress state. So if you can somehow protect against this one noise, you're effectively protecting against all of these noises. And we've shown this using something called robust control techniques. So similar to how there is optimal control, there is something called robust control, where what you can do is you can say, okay, I have this gate, and the majority of the noise comes from, let's say, some process A. I want to protect against process A. What you can do is you can generate algorithmically, you can generate a waveform that protect against noise A, but usually the cost of that is that your gate time increases, which means that you are even more susceptible to noises B and C. So if your robustness against one noise robustness against one noise increases, then robustness against other noises should decrease. That's the usual thing. So here what I'm doing is I'm plotting the fidelity of the gate versus a particular kind of a noise. So here it is the Rabi frequency noise. So as you can see, this red curve is the optimal curve. If I don't think of any robustness at all, you get this red curve. So 1 means that your value is exactly what you think it is. 0.98 means that the experimental device has a value that is 2% less than what you think it is, etc. So the x-axis imitates slight variations in experimental realities. And on y-axis, you have fidelity. So if this curve is steeper, it means that your noise is less robust. If the curve is flat, it means that your fidelity is not changing when the experimental parameter changes. So that's robust. So as you can see, as I increase the gate time here, I go from 1.4 microsecond to 1.6, 2.4, and 3.2. The robustness keeps increasing against the Rabi frequency noise. Usually, if you take these curves and look at the robustness against some other kind of noise, for example, the detuning noise, you should see an opposite trend, because the robustness against other noises should decrease. But as you can see here, I've plotted the same plot for the same waveforms, but for a different noise, delta L, they also increase. This is a very interesting phenomenon. And this happens because all of your errors get funneled into this single quantity, and you're protecting against that single quantity. So usually these robust control techniques are not very useful in experiments. So in this case, they might be very useful. So yeah. And that is the end of my talk. Basically, what we've done is, instead of using UV lasers to implement entangling gates, we use microwaves to implement entangling gates. And there we do some kind of an optimization to see which kind of dressing gives you the best gates. And we show that the robust control techniques can be very powerful in these gates. I did this research with Shiva and Ivan, who are my colleague and advisor. And all of this work was done in collaboration with the people at Sandia, Yuan Yu, Bethany, and Matt. And our paper is on archive right now. You're welcome to look at it. Thank you very much.
Thank you, Vikas, for this wonderful presentation. Now, if people in attendance would like to ask questions, this would be the time to do it. Any questions, any kind? I don't see any questions in the chat anymore. There were some during the presentation.
Yes, yeah.
Also, this was a crystal clear presentation, so maybe nobody has any questions. Okay, well, in that case, I want to thank you once again for agreeing to come over here.
Thank you for the invitation.
Yeah, it was a interesting presentation where you had to switch rooms in the middle of the presentation.
Yeah,
it's okay. So yeah, so with this, this was the last meeting for the Quantum Talent Showcase for this year. I think I'm going to take the screen from you and put it on the other screen to just wrap this up. So once again, thank you, Vikas, for this excellent presentation. Thank you,
All right.
Reza, for helping. And I'm just going to share this. So this was our 22nd session of the Quantum Talent Showcase. We had two presenters, but only one could come because the first one broke her arm, and required surgery. Our next session is going to be in January. It's going to be on the 8th of January. There are two presenters. The first one is going to be Latoya Anderson. She's from Brooklyn College and Simons Foundation. The presentation is going to be a little bit unique in the sense that we are going to focus on the National Society of Black Physicists. And the moderator is going to be Mr. Alan Pierre Louis, who actually made a presentation earlier this year. And you can find that presentation like everything else that we do on the Quantum Talent Showcase. So this is Alan Pierre Louis. Let's see, where's the thing? Over here. So I just wanted to clarify that the sessions, the Quantum Talent Showcase now used to be e-poster sessions, started a long time ago in June 16, 2020. And I have a website where all the presentations are archived. We started recording in 2021. And this year we completed the transfer to the QED-C website, which is over here. And with this, thank you once again, everybody, for attending. Thank you, Vikas, once again. We hope to see you next time, January 8th at, I forgot the time. Let me just mention it and then we'll be done. So it is, I don't know the time. They have to set a time. It's not clear for 2024. So that's basically it. I'm going to stop sharing. Once again, thanks, everybody. I hope you have a good holiday.